So we're going to talk about naming compounds, and the first thing we're going to start with is ionic compounds. So there's a couple different kind of compounds, and the first one, or the simplest one, is ionic. So how do we identify an ionic compound? An ionic compound is made of a metal in the first position and a non-metal in the second position. So you guys remember, you have your periodic table of the elements, and you've got the stair step is the difference between the metals and the non-metals. So everything underneath the stair step is metals. Everything on top of the stair step is non-metals. So a metal in the first position tells us that a compound is what we call ionic. The difference between ionic and the other type, which is covalent, is the fact that ionic bonds are made by exchanging electrons. So metals donate electrons, non-metals take them. All right, let's recall what we already know about ions. Metals are losers. They lose electrons. They become less negative, so they're losing the negativity, and they become positive cations. Non-metals gain electrons. They become more negative, and they end up having a negative charge. When you have a compound, you have positive charges in the front, negative charges in the back, and the total of the positives and the negatives has to equal 0. So a compound is always electrically neutral, so that you have to have as many pluses as you do minuses in a compound. Let's take one that we probably already know. Sodium and chlorine together. Does anybody know what NaCl is? It is, it's table salt. But would it interest you to know that the word salt is a specific term for an ionic compound, so there's more than one salt. The table salt that you use is NaCl, but there's all sorts of other kinds of salt. So if you look on the back of any package that you have, salts are a lot of times used as a preservative. So you can probably find a salt in almost every packaged food that you can find. So it is a general term, and some of the salts behave differently than other salts, but all of them usually act as a preservative. The one that I can't do is monosodium glutamate. I'm allergic to it. That's a type of salt. It's a pretty common one that people don't tolerate well. So let's remind ourselves about sodium. He has one valence electron that he will try to get rid of. When he gets rid of the one valence electron, he will have a charge of +1. Now you might say to yourself, where does it go? Electrons are matter. They cannot be created nor destroyed. So when he gives electrons away, they do not disappear. They have to go to somebody, and that somebody is the non-metal, which is chlorine. Chlorine has 7 valence electrons. He would love to get one more. If he gets one extra electron by taking it from a metal, he can be like argon, and then he's going to be happy. And that's what will happen. So see the pictorial of sodium giving away its valence electron to chlorine. That allows them to both be more stable. Now, if you want to understand what I mean by more stable, look up YouTube videos of what happens when you add sodium to water. Sodium by itself, Na metal, it never comes by itself. We have to isolate it. When you isolate sodium so it's by itself, it is so reactive that it will explode even with contact with the water in the air. So I have sodium back there, but I have to store it under mineral oil, otherwise it explodes. Chlorine, which is Cl2, is a yellow-green gas that will instantly strip all the electrons from the inside of your lungs and be fatal. It's one of the components of mustard gas, which was the reason why biological warfare is illegal, because it's such a brutal compound. So chlorine is so reactive that it'll kill you almost instantly if you breathe it. But put sodium and chlorine together and you get table salt. You put it on your French fries, right? So that's what we mean by more stable. Sodium is too reactive to be by itself in nature. It will always find somebody to react with. Same thing with chlorine. Put them together and they're a very happy sodium chloride. So ionic compounds are formed when a metal gives one or more of its electrons to a nonmetal. When all the electrons are gone, so look at calcium. Calcium has 2 valence electrons. He has 2 electrons to give away. He will give those 2 electrons away to become more stable. So the Lewis dot diagram is, remember we learned dot diagrams? They're actually Lewis dot diagrams. So Lewis is our scientist that we think of when we think of electrons. So those dot diagrams were the Lewis dot diagrams. Remember we gave calcium 2 dots because he had 2 valence electrons. So he has 2 electrons to give away that he's going to have to find somebody to give them to. When he gives them away, he will be calcium plus 2. Now let's go, who could he give them away to? Well, let's go to the other side, to oxygen. Do you see how oxygen has 6 valence electrons, would love to get to 8? So he's got room for 2 extra electrons. If he can grab those 2 electrons, he will be stable. He will have the electron configuration of neon and he'll be happy. So if calcium gives the 2 electrons to oxygen, then they're both happier. And this is what it looks like. So you have plus 2 in the front, minus 2 in the back. That's electrically neutral. That is what we're looking for. Now, what if you were going to make a compound with different numbers of valence electrons or different amounts of electrons that they needed to exchange? Let's try lithium and oxygen. How many valence electrons does lithium have? Let's give lithium his 1 valence electron. Like such. And oxygen, 1, 2, 3, 4, 5, 6 valence electrons. So oxygen needs 2 more. Lithium only has 1 to give. That's why in order to form a compound, oxygen will grab 2 lithiums. Lithium will donate its electrons to oxygen, and the formula for lithium oxide is Li2O. So we can use subscripts to indicate we have more than 1 element if the number of electrons that we need to exchange does not match. So you can use the dot diagrams if you need to. Or, all right, let's do aluminum. Everybody find aluminum? He's in family 3. He has 3 valence electrons. Oxygen only needs 2. So how do we get around this? Well, you can either try to think of the lowest common denominator between 2 and 3, which is 6, right? In order to get 6 pluses in the front, I would need 2 aluminums. In order to get 6 minuses in the back, I would need 3 oxygens. The other thing we can do, so you can kind of match them up, the other thing you can do is cross the charges. I'm getting to the cross the charges. We already did the charges on all of the ions. You should have that at your fingertips someplace, the charges that ions will take. The other way you could do it is the crisscross rule. So let's look at our charges. Aluminum's plus 3, oxygen's minus 2. If you drop the charges down like that, you crisscross them, you'll see that oxygen's 2 becomes aluminum's subscript. Aluminum's 3 becomes oxygen's subscript. Let's look at aluminum chloride. You can either cross the charges down, or you can recognize that I need 3 chlorines to cancel out the +3 from aluminum. Whatever works for you. This is the formula for aluminum chloride. The only thing tricky that you have to watch out for if you do the crisscross rule is that Mg2O2 doesn't make sense. It's called a formula unit, so it has to be reduced down to its lowest ratio. So if you use the crisscross method, just make sure you can't reduce them. Make sure they don't have a common denominator.